Today we will be talking about Talos ALU card design. So let's jump straight into it. Okay, so this will be the structure of the ALU in Talos. We need at least two operands to do any operation, addition, subtraction. We need two input operands. So we need at least two 8-bit registers. I'll call them AL and BL. But remember, we talked about in a previous episode that I want this ALU to do not only 8-bit operations, but 16-bit operations as well. And for that, we would need at least two 16-bit registers. So we add two more 8-bit registers. We can call them A high and A low, B high and B low. And if you consider them to be two halves of a single 16-bit register, then you would have register A and register B. Or you would have four 8-bit registers, A high, B high, A low, and B low. So that's the input operand structure of the ALU. Now, to be able to do subtractions, we need to do an operation in one of the two operands. Let's say these are two 8-bit operands and these are another two 8-bit operands. As we discussed in the previous episode, I want the ALU to be able to do two 8-bit operations in parallel or one 16-bit operation. So these would be two operands of one 8-bit operation and these the other two operands of the other parallel 8-bit operation. To do a subtraction, we need to invert at least one of the operands, which would be the subtrahend. So let's see that the registers B will be the subtrahends. They are the ones that will be inverted in 2's complement notation to create a negative number. And then if you add the A register to a B register that has a negative number, you get a subtraction. So we need hardware for that. I will be using the notion of 2's complement. If you don't know what it is, you can look it up on Google, say 2's complement notation or subtraction based on 2's complement notation, and you get all the basic information there. It's very, very easy. It's just a way to specify a negative number in binary. That's all there is to it. And then if you add something to that negative number, then you get a subtraction. Now, to do that, we need programmable XORs. It's these XOR logic that will invert one of the operands, the B register, which is the subtrahend, if we want to do a subtraction. And that's why it's programmable, because if we want to do an addition, then these XORs, these XOR logic should just let the original number pass through unchanged. And if we do want to do a subtraction, then it will invert the number. It will basically do an inversion of the contents of the register B. And the same happens on the other side as well. Whatever I say for one side holds for the other side as well. For 2's complement, in addition to inverting the binary number, so whatever is 0 becomes 1, whatever is 1 becomes a 0, in addition to that, you need to add 1 to it to create a 2's complement notation of a negative number. But I will show that in a second. For now, we just invert it. So you either invert or not, depending on whether you're doing an addition or a subtraction, and then the result goes to an 8-bit ALU. And the same happens on the other side as well. We have an 8-bit ALU here and an 8-bit ALU there, and you can perform two 8-bit operations at the same time. Now, once these operations are done, the result goes to a result register. So let's call RH result high and R low result low. And like before, if you regard them as the high and the low part of a 16-bit register, then the result register is simply R for result. Now, we need logic to determine whether we are adding, subtracting, or whether we should do two operations of 8-bit in parallel or a single operation of 16 bits. And that's why we need the control logic. I will show it now. Don't get scared. We will walk through it. It's pretty simple. This control logic here will have three inputs that will come from the decoded instruction word of Talos. One is set negative high. If this is active, if we are to set the high part of the ALU, the B high as negative, then This control signal tells the XOR logic to invert the contents of B high, and this carry in here will be high. And what does that mean? When this ALU does an operation, because there is a carry in, it will add 1 to the result. And that's exactly what we need to create a full 2's complement operation. We need to invert the contents of one of the operands, which becomes the subtrahend, and add 1 to it, which is the same as to add 1 to the result. So that's what happens when you set negative for the high part, set negative high. Again, this is a control bit that comes from the decoded instruction word. Now the same thing applies for the other side, set negative low. You will program the XOR logic to invert the contents of BL, and you will add a carry in to the low ALU to add 1 and have a 2's complement notation. And then you just add the results. AL and the inverted BL plus the carry in is an addition that is actually a subtraction, because BL is a negative number, and if you add anything to a negative number, it's like subtracting that negative number. And there is one final control input, set full width, and that's when you want this whole thing here to operate as a 16-bit ALU as opposed to 2 ALUs of 8 bits. When you set full width, this carry out from the low portion will be wired into the carry in of the high portion. And the moment you do that, these two 8-bit ALUs become a 16-bit ALU, and A high and A low become one operand of 16 bits, and B high together with B low becomes another operand of 16 bits. And you can even invert that operand to each half at a time to get a negative 2's complement representation of a 16-bit number. And of course, result high and result low will now be interpreted as one result register of 16 bits. That's all there is to it. It's what on this sheet is on this sheet. Now, of course, when you actually implement it, all kinds of other things start popping up. There is no 74 logic chip with 8 XOR gates. So we need 2 chips here and 2 chips here. We need to break it into 2 parts. So there are 4 chips to perform the inversion. There is no 74 logic chip with an 8-bit ALU. There are only 4-bit ALUs. So we break this in 2, connect carry out from one side into carry in of the other side, just like what we are doing here. And then we have an 8-bit ALU. So we need 4 chips, 2 here and 2 there. So you see the number of chips is multiplying. The registers are all 8-bit registers. It's a single chip per register, so 6 chips. The control logic will require 2 74 logic chips. I'll show you in a moment. And if we want to display the contents of these registers here in LEDs, then it takes several more chips, because we need a driver for the LED. So say a 245 to drive 8 LEDs. And we need another driver. So this goes there and here. And we need another driver to drive the ALU. You don't want any single chip to drive LEDs and drive logic, because when you're driving LEDs, the voltage level may how to say this, you will be draining so much current from the pins that are driving the LEDs here that the voltage levels may fluctuate, and you can't take them as valid logic inputs for another chip, because the voltage level will be fluctuating because of the current drain of the LEDs. In general, all of these 74 logic chips, they expect that when they drive a line, on the other side of the line there will be a fairly high impedance input, meaning that there is very low current draw. So the chip that's driving the line that doesn't have to source a lot of current. and can maintain the voltage level pretty stable. But when you are driving a logic load and LEDs, then the current draw is much higher and the voltage level will fluctuate. And if it fluctuates, you can't guarantee what this chip, the next chip in line, is seeing and how it will interpret the levels, as low or as high. That's the issue. So there will be in the final ALU card a lot more chips than there are blocks in this diagram, but you will know when you look at all those chips that in essence it's just this. It's just what is in here. Everything else is to deal with, LEDs and keeping the current levels and the voltage levels stable, the current levels low, or logic to do bus arbitration, which we'll talk about in a moment. In essence, it's just this, so it's pretty simple. Okay, now we are going to translate the high-level diagram that we've just discussed into an actual circuit using the actual parts that we have available for the design. To do this, I will be using Logic Sim Evolution. This is a simulator. It's open source. It's available for free online. There is a GitHub repository that I will be linking below. It's a logic simulator done by a number of volunteers, but coordinated by a professor of electronics engineering from Switzerland. As any free software, it has bugs, it has limitations, but it's a pretty decent system, especially taking into account that you don't need to pay for it. There is an excellent tutorial about Logic Sim available online for free as well, done by Mark Verdiel. He has a YouTube channel called Curious Mark, if I'm not mistaken, and he made a short tutorial about this that avoids spending enormous time with very basic tasks. So it's a much more comfortable tutorial if you already know your way around the basics of electronics. I will link it in the description as well. This stuff, everything that you're seeing, will be available in the Talos repository, which is also linked in the description. I will be populating the repository slowly with the material that I discuss in each episode. So the material you'll be seeing here in this episode today should be already there in the repository by the time you're watching it. The link is below. You can just download Logic Sim Evolution, install it, and then you can just double click on the files for this circuit, which are available in my repository of the Talos repository, and you can just have the same screen I have open in front of me right now. Let me go to auto so you resize this so we see the entire circuit. This is the equivalence between what you're seeing now and the high-level diagram you've just seen before. These are the 4 input registers. Actually, they are not registers, they are just the lines coming from the registers, which are hidden somewhere above in here, because the registers will actually physically be in another board, in the register file board, and not in the ALU card. They will be in another card. But it's the same thing. These are the lines coming from those 4 registers we discussed. These 4 chips here are the XOR gates responsible for inverting the BL or the BH bytes in case of a subtraction, as we discussed before. These 2 chips here are the control logic we discussed before. They accept the 3 inputs, control inputs we also talked about: set full width, set negative high, and set negative low. There are other 2 control inputs that I will talk about in a moment. These 2 chips here and these 2 chips here are the 8-bit ALUs proper. Actually, they are 4-bit ALUs. I need to connect them together by joining the carry out of one, wrapping around here, and going to the carry in of the other. And so these 2 chips here together make an 8-bit ALU, and these 2 together make another 8-bit ALU. That's all there is to it. And the control logic determines in what circumstances the carry out of the low ALU, which is then processed here and then eventually comes out here, goes into the carry in of the high ALU. And there are different circumstances in which the carry out should be connected to the carry in here, like when you set full width. But the carry in here should also be active, for instance, when you want to do a subtraction, because then these two XOR chips will invert, be high, but we have to add 1, and that adding 1 is the carry in of this chip. Same thing happens here on the other side. The carry in is on this line here, which if you trace it here, it also comes from the control logic, and that's what will determine whether below is inverted and has 1 added to this to make a 2's complement notation of a negative number. That's all there is to it. Now these are the result registers, result high and result low. They are also connected to clock and an active low reset, and the clock and the active low reset come from the backplane connector. I'm using this notation here with these tunnels, not to draw more wires going everywhere, so when a signal has a large fan out, I just use a tunnel notation to simplify the diagram. These 4 logic chips here we didn't discuss before, but they compute the 0 flag. These 2 check whether the contents of this bus here, which is the same as the contents of the register low, they check whether all the bits of register low are 0. And if so, then they activate the 0 flag low, which is this. It goes through a register. This is also a register. It's the flags register, which holds the results of the flag computations. There are 3 types of flags: 0 flag, carry flag, and the sign flag. And that is simply to tell you whether the contents of these 2 registers, there are 3 flags per register, that's why you see 6 here, whether the contents of these 2 registers are 1, 0, and then the 0 flag is active, whether the carry from the ALU here, the carry out here that you see here, going into the flags register, it tells you whether the carry is active, because for instance, if you're doing an 8-bit addition and you're adding, I don't know, 250 plus 10, then you have an overflow, because the result will be higher than 255, and that doesn't fit into 8 bits, so you have an overflow, and then the carry flag low, this one, carry flag low, will be active, telling you that there is an overflow. And the other is the sign flag, which is just the most significant bit of this register, which is bit 7 here, which is also comes from there. Bit 7 here comes down this line, here, wraps around here, and then comes out as the sign flag low, which is here. It goes in there, comes out in here, sign flag low, and it just tells you whether the result is negative. If you've done a subtraction and if you expect a negative result, it tells you whether the result is negative or not. If the result is in 2's complement notation, then the most significant bit is the sign bit. If it's high, it means it's a negative number. And the same thing for the other side: 0 flag, carry flag, and the sign flag. And that allows you to have conditional branches based on whether the operation has produced a 0 flag or a sign flag or a carry flag, and you branch or not branch depending on that. So these 2 bits compute 0 for the low part, and these 2 bits compute whether it's 0 for the high part, and the carry and sign are just bits that are directly available from the ALUs. This is a carry out, this is another carry out, or just as the most significant bit. This is the sign bit high, and this is the sign bit low. That's all there is to it. Now, what about these 2 chips here? Notice that they look different from the rest, and the reason is the following. Logic sim evolution has its limitations, and one of them, at least last time I looked, was that it can't deal with bidirectional signals. Signals need to either be an input or an output. They can't be both, like when you have a bidirectional bus transceiver like the 74245. So there aren't models available for the 245, and I am not using the 245s here as bidirectional bus transceivers. They're only output drivers. and I'm using a 245 instead of a 244 because it's much easier to do a layout with a 245, since all the outputs are on one side of the chip and all the inputs are on the other side. The 244 mixes inputs and outputs on both sides and makes layout more difficult. That's the only reason I'm using a 245, but it's unidirectional, so I just created my own little logic sim evolution model for a 245, which is just a bus driver. It will either assert the internal bus on the high byte. This is internal bus high output, and this is internal bus low output. So that's the low byte of the internal bus, and this is the high byte of the internal bus. And if the output enable here is active, then this driver will assert a value on the bus. Otherwise, it will tri-state this output here, and somebody else will assert the value on the bus. That's how it works. Now, this output enable control signals here come from this control logic here on top, this way, this way, this way, from here. And these are the two chips that form the control logic. And that's why we have two extra control inputs. That's the result high output enable and the result low output enable. And depending on whether these signals are active or inactive, these drivers will assert the corresponding value on the internal bus, or not, or they will just tri-state. Now if we open up these chips here to see the internal logic, yes, this is just 6 X inverters, and I am on purpose using the 7414 as opposed to the 7404 because the 14 has Schmidt trigger inputs with hysteresis, and that's quite important on a large design using multiple cards like this in order to take away some of the interference on the input and to boost the signal. Let me give you a brief introduction into Schmidt triggers so you know why I'm using this chip. Okay, a little intermezzo here for us to talk about Schmidt triggers, which are based on a phenomenon called hysteresis, which is induced by chips that have Schmidt trigger input. The idea is to reduce the effect of noise. That's basically what Schmidt triggers are for. Let me give you an example. Suppose that you have this signal, let me turn on my pen. Suppose you have this signal U. Suppose that this axis here is time, yeah, it's marked here, time. And then the level of this signal goes up and down, as you see here. So it's a very noisy signal, has a lot of EMI, maybe a lot of inductive or capacitive parasitics on the trace carrying this signal. So the voltage levels vary a lot over time. And that's a problem. If you have a single threshold to determine whether U is high or low, 1 or 0, what you get is the following. Here, because this voltage level is below the 1 threshold, the signal is low, and that's what you see here. At this point here, it crosses the threshold, so the signal goes high. And then it stays above the threshold, even though it's going up and then down by quite a bit, it stays above the threshold, and then it crosses the same threshold back low, and that's this. The signal goes low again. And if you follow this, you see that it crosses the threshold here, then here again, then here again, and then there again, and here again. And you have this up and down on the digitized version, which is what the signal will mean for whatever chip is seeing this signal here as an input. And that's a very noisy input then. So what hysteresis is when you create two thresholds, a high threshold and a low threshold, illustrated here in green. So when the signal is here, it's pretty low, so you get the digitized low version. But then it goes, and then crosses the high threshold. At this point here, it crosses the high threshold. Only then is it recognized by the chip, which sees this as an input, as a high signal. Now it continues to be high, continues to grow, and then goes low, and then it crosses that threshold. But now the threshold to go from high to low is another threshold. It's this one here. So what will happen is that the signal has to keep going low, go until it crosses the lower threshold. only then will it go from high to low. You see? So hysteresis is when you have these two thresholds, a low threshold, which is what you use when you're going from high to low this way, and a high threshold, which is what you use when you're going from low to high this way. And if you look at the resulting signal here, the digitized version, it doesn't have these oscillations here, you see? It's a much cleaner signal. If you are going from low to high, even if you have a lot of variation here, it doesn't matter. You have to cross this threshold here. Only then do you get the signal interpreted in a different way. And the same thing the other way around. Once the signal is high, it will stay high even if it varies here a lot. It will only go low again if it crosses this threshold. So Schmidt trigger input chips mean that whatever noise is in the signal will tend to be filtered out. And I will be using Schmidt trigger inverters throughout Talos when we have control signals coming into a card via the backplane. And those signals will go through long traces, they will go through the backplane. There will be a lot of parasitic and a lot of capacitive and inductive parasitics, which increase noise. There will be EMI, electromagnetic interference. So I will be using Schmidt trigger inverters to not only buffer or boost the signal, but to eliminate a little bit, to some extent, reduce the effect of noise, of EMI, of parasitics. That's the idea. Alright, so this is a Schmidt trigger inverter, and for instance the result high output enable signal that comes from the decoded instruction word elsewhere in Talos, coming from the backplane connector, it's inverted before it's sent to the 245, because the 245 expects a active low output enable input here. And this is active high in the instruction word. And then you might say, well, why don't you just change it? Just make it active low in the instruction word and you don't need to invert it at all. Same thing for the other side, you know, the result low output enable. I'm using this NAND gate here actually as an inverter, because if you put the same input on both inputs of the AND gate, of a NAND gate, the output is just the inverted version of the input. So I'm using this NAND gate here as an inverter. And you might say, well, you don't need that either. You just make this active low instead of active high in the decoded instruction word. Now, there are reasons why I'm not doing that. One of them is when you reset the machine, the decoded instruction word will have only zeros. But if those zeros are active, then you have all the bus transceivers in the entirety of Talos trying to assert the same buses, and you have bus conflicts, a massive, gymongous bus conflict. So you want these signals to be active high in the instruction word, so when you reset Talos and they all go zero, that zero will be inverted and will become a 1 here, and therefore these transceivers will not be active. They will not be trying to assert anything on the bus, and everything will still work. That's one reason. The other reason is that all of these control signals that you see here, they all come from some other part of Talos. They don't come internally from this ALU card. So they have to make their way into the backplane, through the backplane connector, through traces until they get here. So by the time they get here, they will be weakened. So you need to buffer them. And one way to buffer them is to invert them through a Schmidt trigger inverter. And then you also have a boosted signal in which you got rid of some of the interference because of the Schmidt trigger. And in this case here, it's the same thing. I'm using this inverter here as essentially a buffer that boosts this signal before it finds its way to the transceiver on board, on the same card as the rest of the circuit here. So these little electrical details are pretty important. You need to manage the signals not only from a logic perspective, but from an electric or an electromagnetic perspective as well. We need to make sure that the signals are boosted when they might be weak. You need to deal with the interference, you need to clean the signals, you need to deal with parasitics. So these are some of the reasons why all the control signals that get into a card always pass through some kind of gate, usually an inverter gate or a pseudo-inverter gate like this NAND gate, to have their levels boosted and to correct some of the EMI, the electromagnetic interference, before they actually play their logic role in the circuit. So that's pretty much it. I am tempted to say a little more about why the results of the ALU always go to fixed registers, the result register, as opposed to being directed to the register file, so you can choose into which register the result goes. Maybe it's not the time to say that yet, it may complicate things, but since I mentioned it, I will give you a very brief explanation, and more details are coming in future episodes. The reason is the following. Remember that this is a RISC architecture, and by the time things get to this card, the ALU card, we will already be in the execution stage of the pipeline, and we will have only one cycle to execute, because in the next cycle it will already be the next instruction. So when we are executing one instruction here in the ALU, the registers A high, B high, A low, and B low will have certain contents, the operands of the computations that we want to execute in this one cycle of the execution stage. So this content will be there, and then during that one cycle the signals will flow through these chips, performing the computations as the signal propagates, and then on the next rising edge of the clock, the output of the ALUs, as well as the output of these logic chips here that compute the flags, those outputs will be latched on the next rising edge of the clock. And in this case, they will be latched by these three registers here, the result high, result low, and the flag register. Now, the cycle after that, the contents of A high, B high, A low, and B low will already change, because they will be the contents for the next instruction. Remember, it's one instruction being executed every cycle. So you do not have the time to steer the results that come out of the ALU to one of these registers, A high, B high, A low, and B low. Because if you do that, you have to address the registers, but then you will change the value of the registers within the same cycle in which you are supposed to be computing the previous value of those registers. So that doesn't work, you see. You have only one cycle. The correct operand will be available in these registers, these four registers of the register file, during that cycle, but you cannot change the control bits as to address those registers in order to be written into by the result of the ALU, because you will be writing into the register that contains the operand of the computation, and you will not be able to predict what's going to happen. It will be a mess. You will compute wrong results. So you have to write the results of the ALU computations into dedicated registers, not the registers of the general purpose register file. They have to be written into local registers here, so you don't interfere with the value of the operands that you were reading during that one cycle you have to perform the computation. That's the only reason. And then if you want to use the result of this computation, which is available in result high and result low and in the flag register, if you want to use the contents of these registers for another operation, then what you have to do is assert them into the internal bus, here or here, the internal bus high byte and the internal bus low byte, and then write them into one of these four registers in the next instruction. So you have to use a register-to-register transfer instruction next in order to make the result of a computation available to the next computation. That's RISC for you. You don't have microcode and state machines to go all this, because every element of the machine is being used every cycle. In CISC, only the elements used by a certain cycle of the microcode state machine are being used, and all the others are being wasted. In RISC, everything is being used all the time. Almost everything is being used all the time. So you cannot reuse one of these 4 registers to store the result of a computation while you are already using their contents as the operands of that computation. Next cycle, the next instruction will be using different operands here. So you have to keep the result in a dedicated register, and then use a move or a copy instruction to move this result from RH and RLow to, I don't know, AH and ALow, or BH and BLow, or whatever combination you want in the next instruction. And then you can do that in the next cycle. So that's the reason why these registers here are local and dedicated. You cannot program the result of the ALU to go into any other register other than the 2 registers that are dedicated to it. And from there you can move them elsewhere in the next instruction, in the next cycle. That's the reason. So this is pretty much it. That's the circuit. But it's still simpler than the real thing, because in the real thing I also want to add the LEDs, so I need to add more of these 245 chips to drive the LEDs, so there will be more chips in here, and I have to add the LEDs, because if that's what will be on the board, I might as well simulate the whole thing as it will be on the board. We can already simulate this. Logisim, I keep saying Logic Sim, it's a Logisim. Logisim has a simulation engine, that's what it's for, it's to simulate things. I can already simulate this, but since what will be on the final PCB will have more components, I want to add these components here in the next episode, and then we will run several simulations to make sure that this works and the LEDs display the correct values and all that, and the logic is working. And once we are satisfied with that, then in the episode after the next one, we will go to using the actual board. I hope it will be back and assembled by that time. In the next episode, we will increase this circuit with LED drivers and everything else, and we will run simulations, and we will look at the schematics and the PCB design, but we will still not look at the actual physical PCB in the next episode. That will be the episode after that. So I hope you've been enjoying. This has been a fairly heavy episode. I hope it's been useful to you. So stick around and it will become more fun soon. In the meantime, take care. Thanks for watching.